All right, let's talk about one of the most beautiful and honestly mind-bending things you can see in sports, a figure skater's spin. We're going to unravel the physics secret that's hiding there in plain sight. You know the move, right? The skater's out on the ice, arms wide, spinning at this kind of graceful, steady speed, and then they pull their arms in, and whoosh! They just accelerate into a total blur. How in the world do they do that? They're not pushing off the ice again, so where does that extra speed come from?
Well, it definitely looks like magic, but I promise you, it's pure physics. It's all about a fundamental rule that governs absolutely everything that spins, from planets and galaxies to a ballerina to the wheels on your car.
So to really crack this case, we have to kind of shift our thinking. All the rules we learned for how things move in a straight line, like throwing a ball, they don't quite work the same way here. We need to learn a whole new language, the secret language of rotation.
And our very first word in this new language is a concept that is absolutely essential for everything that's about to follow. We need a way to talk about an object's perfect balance point.
That point is called the center of mass. And really, you can just think of it as the average location of all the stuff an object is made of. If you could somehow balance a whole complicated object on the tip of a pin, that pin would have to be right at its center of mass.
For a really simple system, like just these two little particles here, finding the center of mass is basically a weighted average. Think about a seesaw. If you have a heavy person on one side and a light person on the other, the balance point, the fulcrum, has to be way closer to the heavier person, right? It's the exact same idea.
Okay, now don't let this formula scare you off. I know it looks a little intense, but all those symbols are really just doing is scaling up that simple seesaw idea. We're just adding up every single little piece of mass and where it is to find that one single overall balance point for the entire system. That's it.
All right, so with that idea of a balance point in our back pocket, we can start to unlock the secret code. And it turns out that the world of rotation is kind of like a parallel universe to the straight line motion we deal with every day. Get this. For every concept we have for straight line motion, things like force and mass and momentum, there is a direct rotational equivalent, a twin that does the exact same job but just for things that are spinning. Let's meet them. So in the linear world, a force is a push or a pull, simple enough. Well, its rotational twin is called torque. Torque is a twisting force. It's what you use on a wrench to tighten a bolt. It's the thing that gets a merry-go-round to start spinning in the first place. Next up, mass. Mass is just an object's inertia, right? It's how much it resists being pushed around. Well, its rotational twin is called the moment of inertia, and that's just a fancy scientific way of saying rotational laziness. It's how much an object resists being spun.
And finally, we have momentum. A moving object's momentum is basically how hard it is to stop. And, you guessed it, a spinning object has a rotational twin called angular momentum. It's the measure of how much spinning oomph an object has.
Now, of those three pairs, the one that holds the absolute key to our skater mystery is that idea of rotational laziness, the moment of inertia. And what makes it so important, so crucial, is that it doesn't just care about how much mass you have, it cares a whole lot more about where that mass is.
So let's just get the official textbook definition out of the way. The moment of inertia is the property of an object to oppose any change in its state of rotation about an axis. In other words, it's just a measure of how hard it is to start spinning something or to stop it once it's already going.
Now, take a look at the formula here. Forget all the squiggly lines for a second and just focus on the mr² part. This is telling us that the moment of inertia is figured out by taking each little bit of mass, m, and multiplying it by its distance from the center, r, squared. And that little squared up there, that's the entire secret. That changes everything. This is the absolute key takeaway. Because that distance is squared, moving mass farther out from the center makes an object exponentially harder to spin. This means in the world of rotation, where you put the mass matters way, way more than how much mass there is.
Let's make this really concrete. Imagine you have a hollow ring and a solid disk, kind of like a frisbee. Let's say, by some miracle of manufacturing, they have the exact same mass and the exact same radius. Now, which one do you think is going to be harder to get spinning?
Well, the math gives us the answer right here. Look at the ring on the left. All of its mass is concentrated way out at the edge, at the maximum radius. Its moment of inertia is I equals mr². Now compare that to the solid disk on the right. Its mass is spread all the way from the center to the edge. And look at its formula. It's 1/2 mr². The disk literally has half the rotational laziness of the ring.
So the ring is twice as hard to spin. Even though it has the exact same mass, its shape, the simple fact that its mass is, on average, much farther away from the axis of rotation, gives it a much, much higher moment of inertia.
And with that one crucial insight, we have all the pieces of the puzzle. We have torque, we have angular momentum, and we have the moment of inertia. We are now ready to solve the skater's secret.
Okay, the final piece is one of the most powerful, most fundamental laws in all of physics, the conservation of angular momentum. All it says is that if there are no external twisting forces, no torques, acting on a system, its total angular momentum, which we call L, cannot change. It has to stay constant. And since L is just the moment of inertia I times the spin speed omega, that product, I times omega, has to remain the same no matter what. It's a cosmic law.
And now, let's put it all together on the ice. 1. Start. The skater's arms are outstretched. Just like our hollow ring, her mass is far from the center, which means her moment of inertia is high. 2. Action. She pulls her arms in tight. She's reshaping herself to be more like that solid disc. By doing this, she makes her moment of inertia low. 3. Result. Because the universe insists that her total angular momentum stay constant, if her inertia I goes way down, her spin speed omega must go way up to balance the equation, and that is the whoosh.
So, when you boil it all down, it's not some trick, it's physics. By simply changing her shape, the skater is actively changing her own rotational laziness. And because the laws of physics are not negotiable, her spin speed is forced to react. In essence, she trades her shape for more speed.
It's an absolutely incredible demonstration of physics in action. And the really cool part is, now that you know this secret, you're going to start seeing it everywhere. You'll see it when a diver tucks into a ball to spin faster in midair. You even see it on a cosmic scale, when giant stars collapse into tiny, incredibly fast-spinning neutron stars. The skater's secret is truly written all across the universe.